Akash.
He is a new student, joined just now.
Yeah, he told he's joined outside SRM ISTID with the help of that
But
ID.
he
I want to
don't know
talk
his
to him.
mail. He don't know how to access his SRM mail. In the
Who is
previous call
talking to me?
from Rishi.
Okay, he's mailing me continuously saying that he's having some issues or something. So I wanted to
No,
clarify matters with him.
in the previous class he was saying that the sir, I am not having the mail, official mail. How can I join it? Something.
All are having mail ID. You know, no. You as a student, you should have clarified matters with him before I do.
Ma'am, he must be in the admission process till now, so that is why he is not having.
Yeah. Shivanesh.
Ma'am,
Shivanesh.
yes, ma'am.
So you checked that attendance marker. Huh? Why did you leave halfway in the class? One
Ma'am,
of the hour
no,
you were
ma'am.
absent for so long.
Ma'am,
Your presence is not recorded in that attendance marker. That's why I
ma'am,
marked you absent.
ma'am, I was attending only, ma'am. I don't know why there is a network problem. I think so, ma'am.
Did you check that attendance marker
Ma'am,
actually?
ma'am, yes, ma'am. That I can't understand that one, ma'am.
See, one of that green portion available checks tells your availability in class. Okay, the remaining portions are blank. I think out of the 2 hours, for 1 hour you were absent, either for first hour or second hour. But you were answering my questions and all. I think second hour blank
Yes, ma'am.
portions
I
are
was
there.
present only, ma'am.
But anyways, based upon that attendance marker only, I will give attendance. Sivanesh.
Okay, ma'am.
Okay, you check it out. Halfway you left or something, your presence is not recorded.
No,
I
ma'am.
don't know why.
Okay, ma'am.
Okay, because of that
Don't I
only I
also
put you absent.
okay, ma'am. I also don't know, ma'am. Why I okay, ma'am. It's okay, ma'am.
So Ujjwal Singh or Utkarsh, are you able to hear me, man? You have to talk to me if you want to sort out your problem. Let me wait for 2 minutes. Only 39 people have joined. See, all those who are present, do me a favor and put your register number and your name in the chat box, okay, for me to mark your attendance today. All right, because I'm not having that attendance marker today, automatic attendance marker. So it will help me, all right, in your free time.
Ma'am, only the last 3 digits would be sufficient, right?
Last,
3 digits of the
yes,
registration.
yes, it's okay.
Okay,
Because in case I don't want to mark anybody absent unnecessarily.
okay, ma'am.
One more time, I'm telling you, those who are present in class, just to type in your register number and name in the chat box so that I will understand that you are present for today alone, because I'm not having system. In system only I can do that attendance, automatic attendance marking. Application is not there in my mobile. Okay, shall we begin the class?
Yes, ma'am.
Yesterday, what are the things that we discussed? Just refresh the things now.
We completed with histories, ma'am.
The entire session, not only history Jesus class we discussed so many other things. Now, what are the other things that was discussed in class yesterday?
Magnetic circuits, magnetic field lines, flux density, permeability, reluctance, magnetizing force, and problems, ma'am. After
Okay,
that,
so this, tell.
construction of the DC machine and a transformer and
Okay,
that
some things I
BH
have
curve.
left. Yes, BH curve we have
Yes,
discussed.
ma'am.
Otherwise,
Bulging of flux line we have discussed, residual flux density we have discussed, and the one more point we have to discuss is coercive force.
yes. Okay, before discussing that hysteresis curve, let me give some similarity or analogy between electric circuit and magnetic circuit. This might be asked in 4-mark question or 6-mark question. So this is the table that represents your analogy. Okay, you know what is the meaning of analogy. So what is the meaning of analogy? Analogy means what?
Relation, ma'am.
Yes, how the two things are similar or different. Okay, that is the meaning of analogy. So we are going to discuss how the electric circuit and magnetic circuits are correlating. Okay, how they are similar or are they different? We are going to discuss. Okay, so in what all factors they are syncing? You tell me. If it is a magnetic circuit, if it is an electric circuit, which law is a basic law in electric circuit? First you tell me, which law
Ohm's
is the
law.
basic physical law? Ohm's law. So this is your Ohm's law that we have written for electric circuit. You know what is Ohm's law? Ohm's law is equal to V is equal to IR, from which you can write I is equal to V divided by R. So there comes this equation. So how that Ohm's law can be made equivalent when it comes to magnetic circuit? What is the relational parameter for I in magnetic circuit?
Flux, ma'am.
Flux. So flux you are having. So voltage is also equivalent to EMF. So what is the equivalent factor for EMF in magnetic circuit?
Magnetomotive force.
So MMF. So what is the equivalent factor for resistance in magnetic circuit?
Reluctance.
Reluctance. So here comes the equivalent relationship for your magnetic circuit. Phi is equal to MMF divided by S. Okay, so again both are matching. Next.
Ma'am, will you share this in GCR? No.
Yes, I will share everything in GCR. Now you listen. Okay, second point. Now we have written the formula for what factor?
Reluctance and resistance.
Reluctance and
Yes, you know
resistance.
the general formula for resistance in electric circuit, that is given by rho L by A. Okay, that is the formula for resistance. Suppose if you want to write the formula for reluctance in magnetic circuit, yesterday only we have derived the formula. What is the formula?
L by mu naught mu r
L
into
by mu
A.
naught mu R A. Okay, so that is also one of the factor by which both the circuits are matching. Okay. Next, third factor, your reciprocal of resistance, that is called as what?
Conductance, ma'am.
Conductance, that
G.
is in electric circuit. And if it is to a magnetic circuit, the reluctance reciprocal is called as what?
Don't know, ma'am.
Reluctance is the opposition. Okay, so permeance is the allowance. Okay, so the reciprocal of reluctance is called as what?
Yeah.
Permeance. Okay, permeance. Next, what is the formula for B that we have written?
5 by A.
5 by A. So that is the formula for magnetic flux density. So this
Yes,
is my
ma'am.
current density.
Yes.
Current density is indicated by J. J is given by what formula? Current
5 by
divided
A.
by area. So this is current density. This is magnetic flux density. Okay, that is also another factor on the basis of which electric circuit and magnetic circuit are analogous. Okay. Now, other things are also there. Suppose if you say current is flowing, okay, you cannot say the same thing about flux. You cannot say that flux flows. Okay, so that is another difference. You can say that current is flowing, but you cannot say the same thing for flux. Flux does not flow. Okay, so that is another thing.
Why,
Then
ma'am?
here R is what? You cannot tell in statement that flux is flowing. Okay, that is the meaning of whatever I am telling you. But in statement, literally you can say that current flows, but you
Okay.
cannot say flux flows. Okay.
Okay,
So
ma'am.
R is practically constant except for temperature. Only when the temperature is varying, R will vary. And similar fashion, S is depending upon what parameter? Reluctance is depending upon what parameter? Resistance is depending upon temperature. With temperature, resistance will not remain constant. Reluctance will be depending upon what parameter? B represents what parameter?
Flux density.
Flux
Flux
density. So
density.
S is proportional to flux density. Next thing is, suppose if you want to set up the current flow, then you want to excite the system. Okay, you want to give it some energy. So if you want the current flow to be continuous, then you have to continuously give it some excitation. You know what is the meaning of excitation? Excitation means input. As long as input is there, current will be flowing. Suppose if you are removing the supply, then will current flow?
No, ma'am.
No, it will not flow. Power cut and all, if it is present, means you are not having current flow to our load appliances. So as long as the energy is there, you will be having current flow. But when it comes to magnetic circuit, what can you say about flux? Energy is required to create flux, but not to sustain it. Once it is created, it will be there. Okay, so that is another difference. Next thing is, last point, you are having electric insulation. So what are the various electric insulators that you have heard about? Electric
Wood,
insulators.
Rubber.
Hmm?
wood,
Rubber.
Wood is there, then
Rubber.
glass.
Rubber.
rubber is there. But do you have any such magnetic insulators? Is it popular?
No,
No,
ma'am.
ma'am. I have not heard
No.
of.
Okay, there is no thing that is called as a magnetic insulator. So that is again a difference. All right. So this is the analogy existing between what two circuits?
Magnetic and electric circuit.
Electric circuit and magnetic circuit. Some similarities and differences that exist between the electric circuit and magnetic circuit. That is an important question. So this finishes off that one. Next, as usual, I have taught you what is leakage flux and fringing. Again, this shows. One more thing I have left out. This is your BH curve. Okay, this is your BH curve. That also I have explained yesterday. So let us continue with the hysteresis curve now. Okay, so this is called as what curve?
Hysteresis curve.
Hysteresis curve. Okay, so in order to develop this curve, hysteresis curve, there is a experimental setup that you have to set it. Suppose if you are having a bar, this is your bar of iron. Okay, bar of iron that is unmagnetized. Okay, it is not yet magnetized. So bar of iron is there, around which you are winding some considerable number of turns of coil, and you are giving the coil a supply. Okay, DC supply, and you are connecting a potentiometer. By varying this potentiometer, you will be able to vary the current flow. If you are varying the current flow, it will be able to vary H. And you are going to draw the curve between B and H. Okay, if you draw it, if B is lagging behind H, okay, for one cycle of magnetization, if B is lagging behind H, then that will be called as your hysteresis phenomena. Okay, that is given here in this statement. So what is hysteresis phenomena?
B is lagging behind
Yes,
H.
if you can see, initially only if H is making one incremental variation, accordingly B will also take one incremental variation. After some time, whatever variation you give in H, it will not be varying. Okay, its increment will be dropping down and it will be saturated. So how much B lags behind H when the material is subjected to a cycle of magnetization is called as what phenomena? Hysteresis. Okay. So how to obtain this hysteresis curve is the question. So for that purpose you are using the setup. So what will the setup contain? An unmagnetized bar of iron or any other ferromagnetic material around which you are going to wind some considerable number of turns of wire, and you are going to connect the wires to terminals to a DC supply via a potentiometer. So if you are varying the potentiometer, you will be able to vary the current. If you are varying the current, H will also vary. And with that, you are going to note down what is B. That is flux density. You are going to draw the curve. So if you do so, suppose if you are slowly increasing I, then H will also increase. Okay, initially, this curve will be taking the path OA. Okay, like this. Curve will be taking the path OA. Alright. Then, after this, at point A, what will happen to the material? Yesterday we have discussed BH curve. No, there are three zones. What are the three zones? Initially it will be linear, then it will be curving out, then finally it will become what?
Saturation.
Saturated. So at a point it will become saturated. Then you are going to reduce H. So how will you reduce H? You have to vary this potentiometer and I you have to reduce. Okay, if you do so, H will be reduced. If H is reduced, then the curve will take back path like this. Okay, now it will flow from A to B. Alright. Now OB. Okay. OB at B point, what is B and what is H? You have to tell me. At point B. That is this point.
H is
This
0.
is the point. At this point B, what is H and what is B? That is my question. At point B. H is 0. What about B? B is having value or it is also 0?
Having value.
Value. What is the value? OB, na?
Yes, ma'am.
Yes or no? OB. Okay, OB. So that OB is called as your what magnetism?
Residual
That is
magnetism.
because of residual magnetism. Okay, residual magnetism. But now H is 0 because you have removed the supply, you assume. So current variation is not there. So H is 0. But there should not be magnetism. But still there is some retentivity property because of which there is residual magnetism. So you want to remove it. Okay, residual magnetism should be removed. What you are going to do is, you are going to reverse the direction of current. Now current will be negative. So H will also be taking the negative direction. Now earlier it was traveling like this. Now it will take H is reversed. Now H is going negative. So now the path will be taken by from B to X like this. Okay. At point X, what is H and what is B?
H is OX and B is 0.
H is OX and B is 0. Flux density is 0. So this is called as my coercive force.
Coercivity.
Okay, that coercive force is necessary to remove that residual magnetism. Okay. Force necessary to remove the retentivity property, a residual magnetism property of the iron is called as what force?
Coercive force.
Coercive force. To remove the residual magnetism property. That is coercive force. Okay. Now, still, considerable portions are not covered. It is traveling like this, then it has covered like this. Then, still if you vary h in the negative direction, then it will go to C point where it achieves negative saturation. Okay, here it is positive saturation, here at C point it will be negative saturation. Okay, now still if you go on varying the H value, now it will take the path CDA and it will complete the hysteresis curve. Okay, alright. So this is how that hysteresis loop is achieved. Okay, and now you know the meaning of residual magnetism and coercive force. So what is residual magnetism
Ma'am,
and what is coercive force? What?
ma'am, to come from point C to D, we have to reverse the direction, no? Current.
Still you are reversing, no? Here fully H is reversed only. Okay, now from negative you will try to push it back to positive. Okay, then only you will be able to get CDA part.
Okay. ma'am.
Okay,
Yes.
understood?
Yes.
Alright, so this curve is called as what curve? This curve is called as
Hysteresis curve.
hysteresis curve. Okay, hysteresis phenomena is nothing but how much B lags behind H when the material is subjected to one cycle of magnetization, that is called as hysteresis. Okay. Alright, so this finishes off hysteresis curve. Now one final thing that you need to discuss about is how you can separate the magnetic materials or magnetic circuits. Okay, so if you refer to this, how you can separate or segregate the magnetic circuits? Tell me, what are the three divisions or two divisions you are having?
Series and parallel.
Series and parallel. That is the subdivisions for composite. So what are the basic divisions? Simple magnetic circuits and then
Composite magnetic circuit.
composite magnetic circuits. Okay, these are the two divisions of magnetic circuit, simple magnetic circuit and composite magnetic circuit. Then if you want to subdivide composite circuits, there are two things. How can you subdivide composite circuit? Series composite and
Parallel.
parallel composite. Okay, for you only simple magnetic circuit is there. Okay, no problems will come from composite circuits. So let us discuss what is the meaning of the simple magnetic circuit, composite magnetic circuit, series and parallel, etc. Okay, so the first picture shows you a simple magnetic circuit. So what can you say about the construction part? Simple magnetic circuit. It is nothing but a toroidal iron ring. Okay, this is an iron ring. Around the iron ring you are having what wound? Some wires are wound. Again, if you are connecting a supply here, it will lead to the current flow. So when current is starting to flow through the coil of air, it will magnetize this iron ring and some flux will be set up. Okay, and here you are having what? There is an empty space, no? So what does empty space have?
Magnetic field.
Empty space is magnetic field. It is having flux set up, but what is the name? Empty space I am telling you. So what is that? Vacuum, free space, or what?
Ma'am, not getting your question, ma'am.
See, this is an iron ring, okay, iron ring, okay, which is also called as a solenoid. But I am not closing it. Okay, here there is an empty space which is equivalent to what? Empty space, vacuum, non-magnetic media. What is the other name for it?
Helix,
Air
ma'am.
gap. Okay, so in between you are having what?
Air gap.
Air gap.
Air gap. So this is my iron ring. Okay, suppose if you are having such a circuit, that circuit is called as what circuit?
Simple.
Simple circuit.
Simple magnetic circuit. Okay, around this you will be winding some considerable number of wires, n number of turns, I will be the current flowing through. When current is made to flow, it will be magnetized, it will be setting of flux lines, it will pass through air gap also. When it is passing through air gap only, you are having two effects that I have explained you yesterday. What are the two effects that you are having?
Bulging effect.
Fringing and leakage flux effect. Okay. And you know what is L pi d, that is your mean length. Okay. I mean, we have derived all these formulas also yesterday. So this is one good example for what type of circuit? A simple
Simple magnetic circuit.
magnetic circuit. Example is solenoidal or toroidal iron ring. Okay. Next. Suppose if you see to this circuit, alright, here you are having how many lengths involved? L1, L2, L3, Lg. Okay, correspondingly A1, A2, A3, Ag. Lg means what? Lg means what? L means what? L means mean length. Lg means mean length of what?
Air gap.
Air gap. Okay. So L1, L2, L3 and all are the mean lengths of three materials. Okay. Here you are using three different materials, magnetic materials. So each and every material is having its own length, own area. Okay. So if you are having such a case, okay, then that circuit will be called as what circuit?
Composite circuit.
Composite series circuit. Okay, composite series circuit. Right. These materials are all connected in series. Okay. So they are having their individual lengths, they are having their individual area, they are having their individual permeability. Alright. But all are connected in series form. Okay, through which the air gap flux will be common. Okay, flux will be taking circular path only. It will be commonly flowing, or you cannot say it will be flowing, it will be passing through all the materials in the same path. Okay, circular path. So because of that, it is called as what type of circuit?
Composite
Series circuit. Okay.
Ma'am, would you please explain it again?
So you are making up a specimen, okay, like this. So I am making this material as a separate one, L2 and A2 and mu R, okay, 2, okay, which is having its own material properties. Suppose if I am joining it with another material, a different one, okay, let this be a different material which is having its own length, own area, own relative permeability. Okay, this is second material. And third material, okay, which is having its own length, area and mu r. In between I am having the air gap also. This is my air gap. Okay, so the specimen is having four different medium. Okay, one is non-magnetic, the other three are magnetic medium. So this circuit, if you are winding up a coil in the same fashion, if you are giving it a supply, it will pass current and it will be magnetically turned on. Okay, and because of which the flux will be setting up, the flux will be taking this path. Like this. Okay, so this is my flux path. So flux is passing through all the materials in a series form. Okay, so that is why this is called as what circuit?
Composite series circuit.
Composite series circuits. Okay,
Okay, ma'am.
now you understood.
Yes, ma'am.
Suppose
Thank
if
you,
you
ma'am.
want to write out the MMF formula for the entire medium now, okay, this is phi SG. So you know the relationship between phi, MMF and S. What is the formula? MMF divided by S is equal to
5.
phi. So what is MMF? MMF is equal to phi into reluctance. Okay, that is how you are cross multiplying. So based upon this factor, you have written this formula. Alright, this is for an air gap, and this is for the all the other three magnetic medium. This is non-magnetic medium. This is a magnetic medium through which the reluctance is common or it's different. Like you are having a series resistance combination. Suppose if you are having three series, resistors connected in series. Then what will you do? What will be the equivalent resistance that you'll be finding out?
R1 plus R2 plus R3.
R1 plus R2 plus R3. This is for an electric circuit. Now you are discussing about magnetic circuit. Now instead of resistance, you are to replace what?
Reluctance.
Reluctance.
Yes.
Okay. So you have summed up. Alright.
Okay, ma'am.
Okay. And you know the formula for reluctance. What is the formula for reluctance? L divided by mu naught, mu
Mu
r,
R.
A. You have substituted. Then you are grouping this phi divided by A as B. Okay, and you are simplifying. Finally, this will be your total MMF for a series magnetic circuit. Okay, only up to this you will have problem. Okay, parallel magnetic circuit and all you will not have a problem. Okay, this is the example for parallel magnetic circuit. It is resembling what machine or what equipment?
Forward, ma'am.
Yesterday I have drawn you the construction of transformer.
Transformer.
So this is representing your transformer only. Okay, so transformer is coming under what nature of magnetic circuit? Parallel, composite or series? Composite parallel.
Parallel.
So whenever you are having parallel combination, suppose if you take this circuit that is an electrical equivalent, what parameter will be considered same? Voltage or current?
Potential voltage.
Voltage will be common. Okay, but here if you are having a series circuit means current will be common. Based upon that you will do derivation. Okay. So this is how we will be classifying magnetic circuits. What are the divisions that are coming under it? One is series and the other one is
parallel.
parallel.
And simple and
Both are coming under composite magnetic circuit. And other combination is simple. Okay, you will have problems coming from a simple magnetic circuit only. Okay. Now let us solve some problems. This is all theory part. Hereafter only problem only. Now two losses I have already told you. What are the two core losses or magnetic losses that you are having?
Hysteresis
What
loss
are the
and
two
eddy
losses?
current loss.
Hysteresis loss and eddy current loss. Okay. One important question is how to eliminate this eddy current loss and how to eliminate this hysteresis loss. So, do you know the answer for it?
No, ma'am.
How to overcome?
Ma'am, by making slow strips.
Slow? Slow what? See, eddy current loss is basically because of the area. Okay, big area of the magnetic medium, if you are having means, if it is made to rotate in the magnetic field, it will be resulting in eddy current and eddy current loss. Suppose if you want to limit this eddy current loss, instead of having a single solid piece, okay, instead of having a single solid piece, you can break it into several thin slices. Okay, you can stack it then together to form a single core. Okay, if you do it in single thin slices and then stacking of all these discs together, then the area will come down. Okay, so if area is reduced, automatically the eddy current will come down. Okay, you know the formula for resistance. Now, what is the formula for resistance? R is equal to
V by I.
rho L by A. Okay, you want to increase the resistance. Okay, if you want to increase the resistance to the eddy current, okay, eddy current is the reason for eddy current loss. You want to minimize the eddy current, so you want to increase the resistance offered to it. So if you want to increase the resistance, what will you do with the area?
Decrease.
Reduced. Okay, so instead of having a single solid piece, you can break it into several thin slices, okay, and you can stack it together, okay, and you can use laminations. Okay, by this you can eliminate what loss?
Eddy current loss.
Eddy current loss. Okay, I'll tell you. To avoid eddy current loss, what is the thing that you will be doing?
Decrease the area.
Decrease the
Decrease
area
the area.
so that resistance can be increased.
Laminate.
Laminations. Okay, laminations. And in between the laminations, you will be using varnish. Okay, some thin slide insulating material will be like paper will be included. So by doing so, you will be able to reduce the area and it will be bringing down the eddy current. Okay, so the losses will be automatically reduced. When it comes to reducing hysteresis loss, okay, how to reduce hysteresis loss? So you have to do what to overcome hysteresis loss? You have to choose the magnetic material with what nature? Hysteresis loss is because of this area only, no? The larger the area, larger will be the loss. So you want to reduce this area. So if you want to reduce the area means you have to choose the magnetic material with what? Narrow hysteresis loop. Okay, this loop should be very small like this. Okay, the greater the narrower nature, you will be having lesser the hysteresis loss. Okay, so this might be asked in MCQs, so you have to remember that.
Ma'am,
So
excuse me, ma'am.
tell.
Ma'am, Dhanush is not able to join the meeting, ma'am. He's telling that he's
He
been blocked.
joined.
Rahul, I joined now.
joined.
Just now I joined. No problem.
Who you told?
Ma'am, I joined,
Tanishka?
ma'am.
Dhanusha?
Yes, ma'am. Am I audible?
Yes. See, now you
I
people
joined.
understood how to eliminate hysteresis loss and how to eliminate eddy current loss. Finally, you tell me these are the two core losses or magnetic losses that you are having. So how will you overcome these two losses? What are
Ma'am,
the effects?
for eddy current loss, we will reduce the area so the resistance will be increased and put on the laminations with varnish.
So how will you be possibly reducing the area? You have, instead of having a single solid piece, you will break that
We
into
will
several thin slices of laminations and you will stack it together, thereby reducing the area. What about hysteresis loss? How will you eliminate or overcome a hysteresis loss? You have to choose the magnetic material with great care, okay, so that its hysteresis area
is
under the
narrowed.
hysteresis loop will be narrow. Okay, the lesser the area, the lesser will be the hysteresis loss. So you have to choose the material accordingly with the some coefficient value. Okay, like silicon you can choose. Okay, all right. So that is it about magnetic and core losses. One problem we will discuss. I think these problems we have discussed earlier. So I will try to give you another problem. So take down this problem. A toroidal air-cored coil with 2000 turns. Take down the problem. A toroidal air-cored coil with 2000 turns has a mean radius of 25 centimeter. Diameter of each turn is 6 centimeter. Current in the coil is 10 ampere. You have to find MMF flux density and find the magnetic field strength and you have to verify B is equal to mu H. Have you taken on the problem?
Yes, ma'am.
What are the things that are given in the problem?
Current, number of turns, radius,
So
and
you are
diameter.
being given with the number of turns is equal to 2000. Okay. Then radius, mean radius they have given 25 centimeter. You have to convert that into meter. So 25 into 10 to the power minus 2 radius meter. Alright. Then the current is also specified, that is 10 ampere they have given. And 6 centimeter diameter of each turn. The coil that you are winding, the diameter of each turn is 6 into 10 to the power minus 2 meter. And you have been asked to find out what parameter. MMF they have asked, flux they have asked, flux density they have asked, and magnetic field strength they have asked, and they have asked you to prove B is equal to mu H. So how will you solve the problem? First thing is you need to find out what is MMF. You know the formula. Unit is ampere turn. So what is the formula?
Into I.
N into I. Number of turns is how much? 2000. Current is given to be 10 ampere. So the answer will be 20,080. That is MMF. Done. Okay. Then you need to find out flux. So how will you find out flux? What's the formula?
B by A. Phi is equal to.
Okay. B is given, huh? B is given, huh?
No.
B is also asked, so you cannot use that formula. But even though you can find
Yes.
out the area, you cannot use that formula. So any other formula can you think of for
Ma'am,
finding
and B
phi?
is mu naught into H, na? So mu naught H by.
Still you need to find H. Okay. And they have not told anything about the mu r value. So you do not know the mu r value. Okay, even though they have given it as an air cooled coil. So any other formula? You know how to find H. You can use that formula also. Let me check up what is B value. You can use that formula. 4 pi into 10 to the power minus 7. They have given air cooled coil only. So you can try it out. Okay, no problem. Other than this formula, you are having any other possibility of finding out phi? Just now I told you there is a relationship that is relating MMF, flux,
S is equal to
and
MMF.
reluctance.
Phi is equal
You
to
can
MMF
you
upon
can
S.
use B is equal to mu naught H. That is also okay. 4 pi into 10 to the power minus 7. They have given air cored coil only. So try it out. H is given by Ni divided by L. Okay. So you know L is equivalent to pi D or 2 pi R. Okay. Where R is given to be 25 centimeter. So first find out
0.25
H
meter.
and tell me what is B. Let me check out the answer.
Hello.
Yes. Do you have the answer? B. What's the answer?
Yeah, I'm calculating.
N into I is 20,000 divided by pi into 25 into 10 to the power minus 2 into 2. So people should not take this much time to give a answer. One simple division. Will it take this much time? What is the answer for B if you are doing this way? That is my question. I have done it by another formula. Nobody has the answer? Nobody has calculated it at
12,734.85.
10,000. The answer is 0.016 Tesla. Then you cannot use this formula. Answer for B is 0.016 Tesla. Anybody got this answer? H is equal to 12,738.
Ma'am, I got it that H answer.
into 4 pi into 10 to the power minus 7. If you are putting, what is the answer that you are getting? Answer should be 0.016 Tesla.
1 minute, ma'am. Ma'am, it is coming at 0.0159.
Yes, 0.016 is the correct answer, around that value.
Yes,
You are
ma'am,
getting
got
the
it,
answer?
ma'am. Yes, ma'am, got it.
All have got the answer?
Ma'am,
Yes, ma'am.
Huh?
ma'am, Tanish
B
might
is
not
equal
have
to
converted it into meter, ma'am. So that he's getting wrong.
mu naught into H. Okay, it is an air cored coil. So mu R is equal to 1, you are assuming. Okay, and then H is found out by Ni divided by L. L is 2 pi R. Okay, R is this 25. Okay, so 25 into 10 to the power minus 2 you have to put. All understood the calculation and you have found out the answer or not?
Yes, ma'am.
What about the rest in class?
Ma'am, 0.0157 coming.
Yes, 0.0157 or 0.016 approximately Tesla. That should be the answer that you should get for B, whatever may be the formula that you use.
Okay.
All got this answer?
Yes, yes, ma'am.
Yes, ma'am.
What about the rest in class?
Yes, ma'am.
Okay, then you are done with finding out B, okay? Then you are done with finding out MMF. B is also over. Then magnetic field strength is also over. Now phi. What is phi?
B by.
B by A. Find it out. Now you
Yes,
just
ma'am.
now calculated 0.016 divided by area. How will you calculate area? Area is given by pi d squared by 4 formula because it is circular cross section. Diameter of each turn is given to be 6. Okay, so pi into 6 into 10 to the power minus 2, the whole square divided by 4 you have to put. Or
Ma'am,
pi r squared. Pi r
yes, ma'am,
squared or
got
pi
it.
d squared by 4. Here it is given in diameter, so I have used pi d squared by 4. You can use pi r squared. Okay, no problem.
7.6.
7 point?
6.
4.48 into 10 to the power minus 5 Weber is the answer. I will show you the answer.
Ma'am, mine is coming as 1.17.
Pi r squared. Okay, so flux is given by this one. You can use your own formula. Okay, I have used the formula MMF divided by S. Whatever may be the formula, the answer will be same only. Area, how much you got? 0.002826 you got,
Yes.
Then
Yes,
it should
ma'am.
be correct only.
Ma'am,
4.48 into 10 to the power
0.0027.
minus 5. Huh?
Mine is coming
This is
at
the answer.
0.00279.
279 is wrong. 0.00448 you have to get.
No, ma'am, area 1.
Okay, area is 0.002826. Calculate
Ma'am,
phi. Phi is what is asked, not area.
0.016 by 4.48.
You are using this formula only.
Ma'am, answer 0.0000452.
Yes, correct. 0.0000, I think.
Yes, ma'am.
448 you will get in Weber. That is 5.
Yes.
Okay. What about the
Yes, ma'am.
others? All got this answer for 5?
Yes, ma'am. Got it.
How much time is left? Shall we discuss one more problem?
Yes, ma'am. 5 minutes. 10 minutes.
10 minutes.
With that, I will finish off magnetic circuits. Okay. Take down this problem. An iron rod of 1 centimeter radius is bent to a ring of mean diameter 30 centimeter and wound with 250 tons of wire. You have to assume relative permeability of iron as 800 and air gap of 0.1 centimeter is cut across the bent ring. You have to calculate the current required to produce a useful flux of 20,000 lines. Assume leakage factor of 1.1. Also find the magnetizing current. That is your question. Take down the question. So whatever may be the problem statement, if you read it, this is a composite circuit or a simple circuit? Composite or series, simple circuit? You people are there? You are able to hear me out? Are you able to hear me out or not?
Yes,
Could you
ma'am.
hear?
Yes, ma'am.
Have you taken on the problem statement? This could you tell me whether it is a simple magnetic circuit or a composite magnetic circuit? Which one? By reading the problem statement. So given here in the question is an iron rod. Okay, some particular radius is bent into a ring. So you are having a ring. Okay, like this. This iron rod that is bent into a ring like this. Okay. Mean diameter is given, radius is given, and it is wound by how many number of turns they have given? 250 number of turns they have given. Okay. And mu r of that iron rod is given to be 800, and in between you are having an air gap of 0.1 centimeter length. Okay, and you are to flux lines also. They have specified 20,000 lines. They have specified, and leakage factor lambda they have given it to be 1% or something. 1.1%, I think. They've asked you to find out current I. Okay. So this is a simple magnetic circuit only, okay, where air gap and the iron rod are coming in series combination. So if it is a series combination means you have to sum up the reluctance, okay, like you are taking equivalent resistance in electric circuit, here you have to sum up the reluctance, okay, and in order to find out the current, first thing is I want current. Okay, I have one notion of finding current, that is by using MMF formula. Okay, MMF formula. MMF formula is given by what? N into I product. Okay, so if you are able to find out MMF, then by cross multiplying, by dividing MMF by N, I will be able to find out my current. Okay, that is the idea of solving this problem. but I know the value of number of turns, that is 250, but I still don't know what is my MMF. And plus I am having two materials here. One is my non-magnetic media here, that is in the form of air gap. Okay, this is my air gap, that is my non-magnetic media, and here an iron rod is there, that is my magnetic media. So I have to find out the total MMF by summing the MMF of iron and the air gap. Okay. So by doing so, I will be getting the total MMF, and by dividing the total MMF by number of turns, I will be able to get the total magnetizing current. So how I find my MMF of iron and how I find my MMF of air gap is the question. So how will I do that? Tell me. MMF of air gap. MMF of air gap, what is the formula? I could use flux into the reluctance of the air gap.
Reluctance.
Okay, so flux is given to be 20,000. So S of air gap is given by L divided by mu naught, mu R and A. Okay, so by using this formula I can find out S, where L is equal to 0.1 centimeter. Then mu naught is 4 pi into 10 to the power minus 7. Mu R is 1. And again area is also given, that is again 1 centimeter radius. Okay. So with that I can find out the air gap MMF. Okay. Then I need to find out the MMF of iron. Okay. But the mean length of iron I do not know. Okay, mean length of iron is not given. Air gap mean length they have given. Okay, so with that I can find out the area. I can do calculation of reluctance of air gap. Okay, but the mean length of iron gap, mean length of iron is not known to me because they have not given that directly. So for that, one formula is there. This formula. So what is the formula for it? They have given the mean diameter to be 30 centimeter for the iron ring. Okay, so this is the iron ring diameter. Okay, that they have given. So just if I want to take the mean length of iron alone, I know the mean length of air gap, that is 0.1 centimeter. So if I take the difference, I will be able to get the iron rod's mean length alone separately. So if I find that out, I can substitute in the formula for reluctance. Then I can find out the reluctance of iron. Then as usual procedure, I can sum up the MMF of both by using this SI plus phi into SG. Okay, and I can find out the magnetic current. Okay, this is the procedure. Okay, plus one more thing that needs to be found out is, okay, they have given some leakage factor is equal to 1.1. For air gap, the flux is known to me, that is 20,000. Alright, but I don't know the flux of the iron path. So in order to find the flux of the iron path, I have to use up the leakage factor. Okay, so this is how I will be solving the problem. Okay, the same problem plus one more problem I will do it in the next class. Alright, now there is no time. So I will do this problem plus one more problem in my next class, plus other topics will be discussed. Okay.
Okay, ma'am.
Yes, ma'am.
Okay, all have put in your numbers and name in your chat box.
Yes, ma'am.
Yes, ma'am.
Yes,
Okay.
ma'am.
See, whoever has pressed the recording button will stop recording.